Okay, welcome back, guys. This is going to be hopefully a quick video about Unit 6, Lesson 5. And in this lesson, we're going to look at graphs of reciprocal trig functions, right? And mainly cosecant and secant. Cotangent we addressed in the last lesson notes. So, please remember to get in touch with your teachers if you have any questions about this stuff, or write up questions that you have on the shared doc. I hope that'll be a better collaboration tool for you guys as we go forward. Okay, so this slide's going to have some general characteristics of both the cosecant and the secant functions. So first of all, cosecant, right, abbreviated CSCX. Let's remember, right, that this is really equal to 1 over sine x, okay? Because of that, right, now we actually have, a form of a rational function. Now, it's not the way we defined rational functions before, but we have a trig function in the denominator. We know if this is going to be 0, we have vertical asymptotes or maybe holes or, some kind of discontinuity. So if we go through these characteristics, first one says there are vertical asymptotes. Well, that's because cosecant x is equal to 1 over sine x. So whenever sine x is equal to 0, this whole thing is going to be undefined. Cosecant x is going to have a vertical asymptote. Okay? So that asymptote occurs at pi, and it repeats every pi unit. So if we go over to this graph here, you can see here's x equals pi. Well, there's a vertical asymptote there, because hopefully remember the sine of pi is 0. The sine of 0 is also 0, so there's a vertical asymptote here. The sine of 2 pi is also 0, so there's a vertical asymptote here. Okay, so that's a key feature, is this thing's going to have vertical asymptotes, and for cosecant, it's at pi, and they repeat every pi units. Second thing, the period of the whole graph is 2 pi. Well, that makes sense because we know that the period of sine of x is 2 pi, so the period of this whole thing is going to be the same, right? We have a positive portion here, then a vertical asymptote, a negative portion here. Once we jump over 2 pi, we're going to have this same, U-shaped repeated over here. Okay? There's no amplitude, just like for tangent, because they go on forever in vertical, in the vertical direction. And then here's kind of a nice feature. The maximum values of sine x are the minimum values of the positive sections of cosecant x. Okay, so what does that mean? Well, if we were to graph the sine x function, right? Well, we know that sine of 0 is 0. Hopefully remember that sine of pi over 2 is 1. Okay, so the sine graph's going to start like this. The sine of pi is also 0. Okay, so that graph will come down. The sine of 3 pi over 2 is actually negative 1. And the sine of 2 pi is back to 0. So if we look, these graphs, and by these I mean the cosecant graph and the sine graph, they touch at only one point. They touch right here, okay, where sine has a maximum. Where sine is a max, cosecant's a min. Another way about thinking about that is that 1 over the biggest number is the smallest number, and 1 over the smallest number is huge, right? So in this case, 1 over 0. When sine is 0, the cosecant graph is huge. Then if we look here, the minimum values of sine x are the maximum values of the negative sections of cosecant. Okay, so what does that mean? Well, here's where sine x is a min. That point, right at 3 pi over 2, negative 1, that is the max value of the negative parts of cosecant. Okay, so really, you could just graph a sine function. Wherever the sine function is 0, you make vertical asymptotes, right? Wherever the sine function has a max, cosecant has a relative min. And whenever sine has a min, cosecant has a relative max. All right. And yeah, we mentioned this before. The x-intercepts of y equals sine x are the asymptotes for cosecant x. So again, when sine x is 0, here, 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 and keep going, cosecant has vertical asymptotes. Final thing with cosecant, the u-shapes of the cosecant graph are tangent to its reciprocal function sine at sine's max and min locations. Okay, so that's basically just saying that they touch when sine is a max or when sine is a min. Okay, let's go for one more, then I'll stop and make a second video with the example. All right, secant x. So very similar characteristics, but things change a little bit because secant is equal to 1 over cosine. Okay, so again, we have vertical asymptotes, but now the asymptote will occur at, this should be pi over 2. So we missed that. Let me write that in. That's pi over 2. And it still repeats every pi units. Okay? So cosine of pi over 2, well, that's 0. So secant has a vertical asymptote. Go pi units to the right to 3 pi over 2. Well, we know that cosine of 3 pi over 2 is 0 also. Secant has a vertical asymptote there. Okay? And like before, I'm going to try and do this a little bit faster. If we were to plot the cosine x graph, something like this, right? Well, when cosine has a max, secant has a relative min. That occurs right here and right here. Well, actually, I'm not being very accurate. It should be like right there, right? Okay, so cosine max, secant relative min, cosine max, secant relative min. When cosine has a min, secant has a relative max. All right? And then the other thing, let's go a different color. Let's go pink here. So when cosine of x is equal to 0, right there, the secant graph has vertical asymptotes. That bothers me. Let's go back and make that a little bit straighter. Okay? So you can read the rest of these characteristics, but it's really the same idea, right? And I think the most important thing is to understand, okay, can I graph this part? And then from there, can I make the adjustments to make the graph of this?